looking forward to hear the webinar by Hamod, as he has a lot of experience cutting with iMachining, so it should be an interesting webinar. Before that, I just want to say a few words about SolidCAM 2016. I have sent to many of you, all of you, the information about SolidCAM 2016. I mean, you have it. Now you are looking here at our new website. If you log in, you have to be logged in. And once you are logged in, you can go to the reseller area in the website. It's under company, reseller area. And here is the reseller area where you have the reseller scoreboard that shows all the time at what rate you are in subscription, in iMachining, in HSS, HSM. This is updated, by the way, daily. It's connected to our Salesforce system according to your sales. And you have here a button that says SolidCAM 2016 Preview and Info. Here you could download a pre-release of 2016. And we have put here for you a presentation of what's new. I will go through it very quickly. Basically, the most important thing in 2016, as you know, is the advanced mill-turn solution. So we have all the information about the advances in our mill-turn, and also, obviously, there are also advances in the other technologies, 2.5D milling, in the definition of the geometry, very powerful new options. We have done very nice work in advancing the subject of transformations. We'll make webinars about this subject and explain in depth. Also, we have some advances in turning, changes in compensation to remove additional movements that were not liked by many of you, how to approach to compensation, and some other general improvements in the system. We have also put there, I mean, many of you are having events of what's new in SolidWorks 2016. So what I suggest in these events is you can use the PowerPoint presentation, or we have put some very, very nice parts for you that you could download and show the simulation, at least. I mean, here you have three very nice parts. But I remind everybody that to run these parts, you need to launch SolidWorks 2016 pre-release. I assume all of you can download this pre-release of SolidWorks, like we did. And the parts that we put in our website, you could load them with SolidWorks 2016. So here we have one of those parts I showed you. You can basically, if you don't want to work too much in your presentation days, you can just load the part, as I did now, and make machine simulation. Very nice machine simulation. These are advanced mill-turn parts. Let's see, for example, one of these parts, how it looks. So as you see, it's a very interesting advanced mill-turn machine. Let's start the simulation. As you see, we use all the parts of this complex machine. Let's run it again. And this is really a very advanced use of these machines in our mill-turn solution. Let me load also the other part and show it to you. Here also we show the manufacturing of this U-drill. Let's see the machine simulation. Here we have a Wilhelmine 508 mill turn machine. And again, let's see shortly the simulation. As you see now in SolidCAM 2016, you are able, through the VMID, to define all the accessories and components of these complex machines, and everything is shown in the machine simulation. Really a great advance. So, in all your events for SolidWorks 2016, please show SolidCAM 2016, show the presentation, show some machine simulation. I think this will be a very good addition to what you are showing about SolidWorks 2016. And we will obviously keep updating this pre-release until we do this release as planned toward the end of this month. Thank you.
Thank you, Emil. And let's start the webinar, iMachining for Superalloys and Hard Materials by Amod Unkar. Amod, you are presenter now, and you are unmuted.
Thank you very much, Eddie. Good morning, good afternoon, and good evening. Sorry for my voice. I'm having a problem with my throat. So in between, if I go silent, it was because of my throat. So today, we're going to do a very interesting webinar. This is about iMachining for superalloys and hard materials. Now, superalloys are also called as exotic materials like titanium, inconel, stellite, hastelloy. Also, we have recent addition of tungsten carbide, and of course, our old stainless steel that's there. Ever since their introduction many years ago, the heat-resistant superalloys, or HRSA, as they are called, have always been extremely difficult to machine. They have always been a machinist's nightmare. But of late, there have been a lot of developments in machinery and equipment, the holding equipment, fixtures, and tools, and of course, software, the ability to cut the part with a different kind of machining strategy. All of these have made machining of these materials much more easier. If you look at the HRSA materials, they are primarily used in aerospace, in energy, and also recent addition is the medical devices. For example, the implants. The orthopedic implants are all titanium implants because they are very light and extremely strong. They mimic strength better than bone. So they are used also in the medical industry. Now, these materials are metallurgically composed to have high strength at extremely high temperatures. And therefore, the stresses that are generated with machining are also very high. Now, if you look at these materials, the heat-resistant superalloys, they're basically put into three main groups. The first group is the nickel-based alloys, iron-based alloy, and the cobalt-based superalloys. They have this unique ability to perform the capability of these materials is to perform at near melting point. They go very close. So they're used in applications where they are going to be subjected to very high heat. And now this particular unique ability also makes it extremely difficult for machining. This is one of the reasons why they are so difficult to machine. You'll also notice that companies that machine these parts have stronger machines. They have much higher torque. They have a much higher power on their spindle, and above all, they have more RPM. There is a general belief that the power that is needed to machine these alloys is almost double that is needed to machine alloy steels. For example, you would need a cutting force of almost 4,000 newtons per square meter for super alloy compared to a 2,500 newton per square meter for steel. So naturally, your machine has to be that strong to machine these components or these parts. These alloys basically are ductile. Okay, their fatigue resistance, hardness, and toughness at high temperatures combined, they all put together, they give amazing amount of wear combinations for the tool. So you will see that when you're machining Inconel or when you're machining titanium, there are two possibilities. For example, titanium, it's highly reactive. It has extremely high chemical reactivity. So it gives this unique edge buildup on the tool. And once the edge buildup starts on the tool, trust me, in the next minute, you're going to have the tool completely disintegrated. On the other hand, Inconel, it's a pretty sticky material. So the wear mechanisms of the tool undergoes, dynamic changes. The edge of the cutting tool is exposed to considerable amount of mechanical stresses, strain, and heat while machining these alloys. So, first of all, the main characteristic of these materials are they are extremely, they have very poor thermal conductivity. So if you look at the challenges that are there in machining these materials, is that one, because of the process that is being currently followed by conventional systems, I'm not talking about iMachining, but conventional systems, is that there is a major amount of chip thickness variation, which means the mechanical and thermal stress on the tool is changing dynamically every point. So you have the chip thickness variation. You also have high heat stress because these materials have low thermal conductivity. Therefore, the material or the stock doesn't absorb the heat, but passes on this heat back to the tool. So they have got very high heat stress. They develop very high heat stress. And because of the thermal reactivity and edge buildup and stickiness of the material, the tool wear is very high. Okay, if you take a cutting tool, let's say from Iscar for machining Inconel, the tool life would be not more than 20 to 22 minutes. Whereas for the same tool or a similar tool for machining steel, the tool life could be as high as 90 to 100 minutes. So there is a major variation in the amount of tool wear that happens when you're machining Inconel, when you're machining titanium, or even you're machining the regular steel. So the tool wear is very high, and this is one of the biggest challenges today being faced by the industry. How do we keep the tool life higher? How do we keep the cost of the tool lower? And the most important thing is deformation process that undergoes dynamic changes, because most of these materials have this unique ability to work harden. That means you cut one portion, and by the time it moves to the other, the previous cut portion would have already hardened. This makes it extremely difficult for the subsequent operations, or within the same operation, the same cuts to start cutting. And above all, how do you get the right cutting conditions? Now, these are some of the challenges, or the major challenges today being faced by anyone who ventures into cutting superalloys. To cut any part, you will need all of these. So they greatly influence your cutting process. First of all, you have a CNC machine. Now, on a CNC machine, the construction of the spindle, the power of the spindle, the RPM, the acceleration and deceleration of the axis, the control, all play a major role in how your part is being cut. Why do I talk about spindle power, the spindle construction? Because you need to have a strong spindle to cut these parts, because number one, they're sticky, number one, they are hard. So you need to have sufficient power on your spindle. I talked about another thing of acceleration and deceleration. Your acceleration and deceleration has to be very fast, because I told you that when you looked at some of the challenges that we have this unique ability of work hardening. So you have to be very quick to re-enter the zone much faster than you would do with the same machine cutting steel. So your acceleration and deceleration has to be very fast to leave the material and to re-enter the material again. If that is slow, then you're giving a chance for the material to work harden faster. So you're allowing it to work harden and then try to cut the part again, which becomes much more difficult. The other major influencer here is the cutting tool itself, because that's the one that is actually doing the cutting. That's the one that is taking the heat. That is the one that is taking the stress while the part is being cut. So the cutting tool has to be capable enough to cut the material and withstand the mechanical and thermal stresses that are being developed at the cutting edge. So the geometry of the cutting tool is pretty important. The type of cutting tool is pretty important. We are going to see what kind of tool is much better for cutting these materials. We'll see that in the subsequent slides. The other important thing is how you're holding the tool. I've seen in many cases people taking the tool, they take a very expensive tool, they have a very expensive machine, they're cutting titanium, but they end up using collets instead of other regular holding mechanisms. Collets, by the way, have a very small holding area when you consider the length that's being held to clamp the particular tool. It's either just 1D or even less than 1D. So collets are a big no when you're cutting these materials. The other reason why collets are a big no is because when you're cutting titanium and when you're cutting Inconel, you generally tend to use high helix cutters. And high helix cutters, when they come in contact with material, they have got this ability, the material has this ability to pull the cutter out of the holder. So your clamping force on the tool has to be extremely high, and this just cannot be achieved by collets. If you're going to use collet, trust me, in the very first cut, the tool is going to be out of that collet. So you have to use suitable holding devices for the tool. The other influencer in this case is the fixture itself. How you're going to hold the material counts in a big way on how effectively you're going to machine this part. Of course, the best way to hold a part is always in a hydraulic vise, but not every time you have this liberty of holding a part in a hydraulic vise. Sometimes you have to depend on a fixture because you need to machine on several sides, so you can't use a vise. In that case, you have to have a fixture. So your fixture design plays a major role in how aggressively you could cut this part, or how easily you could cut this part. The fourth influencer in this case is the cooling itself. The question here is whether to use air, whether to use fluid lubricant. This question will be answered in my subsequent slides, but the important thing here to mention is the design of your cooling will determine how effective your cutting is going to be. And I'm going to show you a design of cooling that I had the privilege of getting it from Mickey. So I will also share with you later on, if you want, the manufacturer of such cooling rings, so that you could suggest them to your customers. And last but not the least is the CAM system itself. I'll just open up a small thing that I got from Sandvik. It's about machining super alloys. And they talk about the processes that need to be used for machining titanium Inconel, and other superalloys. If you look at this whole document, when you look at the processes they talk about, you can see that all of this is being replicated from iMachining itself. Trochoidal cutting, cutting the corners, profiling, and most important, if I go down to the feed rate management, they also talk about the peripheral and central feed rate control of the tool. This is something which is you will never find in other softwares. I'm going to show you all of these features inside iMachining, and this is what Sandvik talks about today when you talk about machining superalloys. Okay, let's get back to our presentation. So, we're going to talk today about several things, and the major one is iMachining itself. We all know, I don't have to explain to you again what iMachining is. In fact, for customers, I had to explain a lot about iMachining yesterday, but we are not going to talk much about the basics and other things, but we know that iMachining today stands out in the market when it comes to machining superalloys. The replicas of iMachining are simply able to generate only a pattern. But what makes iMachining stand out is the fact that it generates its own cutting conditions, number one, and then uses the cutting conditions to adapt those conditions to the pattern of tool path that has been generated. And most important is the cutting force. Now, in steel, in aluminum, the cutting force may not play a major role because you could make a small mistake in the cutting force calculation and you could still get away. In aluminum, the tendency is like you make a mistake, a big mistake, and you still can get away with it because it's soft. Steel, 16 mm CR5 and 20 mm CR5, a small mistake, you will see some small changes in the spindle load and you will still get away with it. With titanium and Inconel, a small change, a small variation in the cutting force that's acting on the tool can be catastrophic for the tool itself. A small change and you'll have a tool disintegrated right in front of your eyes. So the cutting force is one of the major things what iMachining gives to the machining world, constant cutting force principle. This is a slide that I took because it just makes sense for us to revisit what iMachining is all about. It's a revolution in CNC machining. It dramatically reduces your cycle times. You save 70% and more. When you say 70% and more, it's extremely applicable to titanium, Inconel, and the hard materials, because we have seen over the last couple of years that harder the material, more is the saving. It's like directly proportional. If you have a hard material, you have got higher savings. So when you look at all those success stories of titanium Inconel on our website, you will see a minimum of 70%. Nobody talks anything less than 70%. It's always 70 or more. You increase the tool life because you take the full flute length as the depth of cut, number one, so that the wear that happens on the tool is uniform. And number two, the most important thing is we generate constant chip thickness or constant cutting force on the tool that dramatically increases your tool life. Using these two, we machine hard materials much better or way better or miles ahead of our competitors in terms of machining hard material. Now the best part, you must have seen the difference between iMachining videos. Let me talk about videos, okay? iMachining videos and all the other competitive videos that you see on YouTube. If you observe very closely, you will see that most of the competitors never have shown you a video of a tool less than 10 millimeter. They always talk of 10, 12, 16. So they show bigger tools taking bigger depth of cuts and more aggressive cutting. But when you look at iMachining, you'll see that there are several videos that show machining with small tools, 4 diameter, 6 diameter, 2 diameter. This is the fact that combined with our technology wizard, the force that we generate is capable enough even for, or good enough even for small tools, makes us stand apart. Okay, so we can use smaller tools more effectively than any of our competitors. And most important, the programming productivity. You know very well that iMachining doesn't take much of a time to learn. It doesn't take much of a time to start using. So it has extremely high programming productivity, and being very easy to use, it has got the shortest learning curve in the industry. The same iMachining 2D, when combined with the slicing and the step-up principle, we have iMachining 3D. So we can use both 2D, iMachining 2D, and iMachining 3D effectively to machine any part, any material, and under any condition. So that's the gist about iMachining. So iMachining combined together with the unique toolpath and unique wizard that we have makes us an ultimate solution. The difference between us and the standard offset toolpath is that in standard offset toolpaths, you know that just means take an outer contour and keep collapsing it with a certain offset, which is nothing but the step over, until it comes at the center and finishes the profile. In such cases, if you look when it goes into a corner, it actually generates extremely high cutting force on the tool. To lessen this cutting force, what we do is we reduce our depth of cuts. And even then, the force acting still doesn't reduce much, which I'm going to show you also a very interesting experiment carried out with a university where we have measured the kind of cutting forces that are acting on the tool, axis, and everything, and documented it. So you could actually show it to your customers also on the difference between the forces of iMachining and conventional cutting. So if you make a summary of what iMachining is about, we generate smooth tangential toolpaths, we have controlled stepovers, and exact stock machining. All this put together with our unique technology wizard creates unbeatable toolpaths that can machine almost any material under the sun. Okay, that includes tungsten carbide. So if I summarize the main features of iMachining, we've got a unique toolpath pattern. We generate optimum automatic cutting conditions. Based on the above 2 points, we generate constant cutting force, and we are the only solution currently in the market today that can predict vibration and chatter even before you take the toolpath down to your machine. So we give this feedback to the user and give him the ability to correct and reduce the chance of vibration and chatter, which can actually cause the tool life to go down. We give him that ability to correct it way before even the machining starts. So all these 4 features put together actually generate or make SolidCAM's iMachining stand out in the market. Right. Now, if you actually take iMachining and go to your cutting tool vendors, because they are the ones who are in the forefront of machining. So if you take iMachining and go to your cutting tool vendors, the complaint that most probably you'll hear from them, unless they know iMachining in depth, is that you guys generate extremely high cutting speeds. Okay? Why do we generate these extremely high cutting speeds, which are 4, 5, or even 6 times more than conventional cutting speed? That's because of this unique person called Carl Solomon. We follow his theory to the core, which is also called as the Solomon's curve for high-speed machining. This was developed in 1931 when there were no machines, CNC machines really existing. So the concept of HSM actually goes back to 1931. What did he do? Let me make the graph here. Okay. So if I drop a graph, and my y-axis is the temperature, and this is the V, the cutting speed. What is actually taught to us by the cutting tool people is that you always have a linear curve, which means if you increase your VC, your temperature goes up. So they assume that the curve is linear. However, what Carl Solomon discovered was something different. He also started off with a lower VC, and as he increased the VC, the temperature started increasing. That's what we know. But at a particular VC, which was like 5 to 10 times higher than conventional machining, he actually saw the temperature plateau and actually drop. Okay, so the temperature started dropping as the VC went beyond 5, 6, 7 times. So the cutting edge temperature started dropping. So let's assume the temperature is about 900 here. So at 900, we have got a certain VC. For the same 900, here we have a VC that is 5 or 7 times faster or higher than that conventional VC. And this is where is the zone which iMachining is situated at the moment. So we are at this zone. So when people say your VC is very high, you use extremely high VCs, our tools cannot withstand these kind of cutting speeds, then you have to show him this particular slide and tell him, look, this was already demonstrated in 1931. We are in 2015. So your tools are very much capable of attaining this VC because the temperature, the cutting edge temperature, is almost the same as what it would be at your conventional VC. So the Solomon's theory is very important because that's the crux of high-speed machining. Unfortunately, this was not accepted until quite late, about 5-10 years back, that this theory started gaining acceptance. And we have used this theory very widely inside iMachining. We follow it to the core. Okay. So we are talking about a transition range or a cutting speed range, which are in this zone, in the black zone, for steel, for titanium, for nickel alloys. What we are basically saying is that if you are talking about 100 for titanium as a cutting speed that you say is the best that your tool can achieve, we have seen in several places that iMachining can touch on titanium without any issues 250, which will certainly make eyeballs roll for all the cutting tool vendors. They say 250 for titanium is impossible. But when you show them the cutting on 250, they believe you. And that's the game changer with iMachining. Now, putting this high VC is no big deal because even probably our competitive CAM systems can do. They can put high VC, generate a high RPM, and generate a high feed rate. But will that really work? No. What makes iMachining stand out is the fact that even at high cutting speeds, it is able to maintain extremely low cutting forces on the tool. And this is to our engagement angle concept that we have inside iMachining that makes the load on the tool extremely low and constant. I'm going to show you this. You should have this presentation because it's a very important presentation. It's like a proof of pudding. Okay, so towards the end, I'm going to come up with this. So how does it actually work inside iMachining, especially on these super alloys? For that, we need to understand the temperature balancing process in high-speed machining. So if you look at the temperature balancing stages, when the first contact of the tool happens at extremely high cutting speeds, the edge temperature rises because more heat is produced, and more heat means higher edge temperature. And because of this rise in the edge temperature or the contact temperature between the workpiece and the tool, the stock material or the workpiece material gradually moves to a plastic phase. So there's a transition from solid to plastic phase. In this plastic phase, the moment it is into the plastic phase, automatically when there is a next motion of the tool entering the material which is already into plastic phase, you need less cutting force. That means the cutting force is reduced because there's less resistance to cutting. Because the cutting force is reduced, less energy is expended. That means less energy is spent to cut this. Because less energy is expended, it means you produce less heat. And because less heat is produced, the temperature goes down. That is the concept of iMachining. It's a very beautiful concept. It starts with rising temperature because of the high cutting speed. The material goes into plastic state because of the high heat. Once in plastic state, the cutting forces are reduced. Because the cutting forces are reduced, less energy is expended in the cut. And because less energy is expended, the heat comes down. You expend less heat. And because the heat is less, the cutting edge temperature goes down. But does it mean, like what happens in every story, that your last process is over? Does it mean that it goes back again to the first one? Actually, no. That's the beauty about this process. The beauty about this process is, as this last stage is crossed, okay, the entire process goes into a state of equilibrium. Okay, once it goes into a state of equilibrium, only this fellow remains, which means that you have got a lower cutting edge temperature when it's cutting in the entire part. Of course, there are several things that are needed to maintain the equilibrium. You can't have equilibrium without no cooling, because cooling is very important here. If the cooling is switched off, your story is likely to go back to the first stage. And if it actually goes back to the first stage, you're going to have a catastrophic effect on your tool. Your tool is going to simply disintegrate because it can't take this change in thermal stress on itself. So it's important that this process being extremely sensitive to temperatures, you must give everything, you must control this process to avoid this process being collapsed. So it's very important to understand this particular diagram, or what we call as the HSM temperature balancing process, where it starts from rising temperature till the temperature goes down, and then it goes into a state of equilibrium. How does this happen, or how does the force on the tool go down? We know very well that iMachining comes up with this unique ability to maintain cutting angles that vary from minimum to maximum. And as the cutting angle varies, iMachining intelligently varies the feed rate in order to maintain constant force on the tool. So if you actually look at any cutting that happens in iMachining, and this is actually a very good sales tool, is to collect the chips, okay? To collect the chips, and at the end of the cut, display the chips in front of your prospect or in front of your customer and ask him to measure each of this chip. He will be surprised that the chip thickness of every chip, irrespective of whether it cut in the corner or whether it cut on a straight line or a profile, it's the same. So when he says the chip looks to be the same, you should tell him, look, the chip is same means what? Means the load on the tool has been constant throughout the cut. This is a USP. If your load is constant, you can ask any cutting tool vendor in the world. He'll say that my tool life is depending on the amount of mechanical and thermal load that you're putting on the tool. So if you're going to guarantee me a constant load, I can guarantee a higher tool life. And this is exactly what happens. Your tool life actually goes up with iMachining. So the underlying principle is that we maintain a constant load by varying the engagement into the material and by changing the feed rate at different engagements. For example, if the engagement is more, our feed rates will drop. If the engagement is lower, the feed rates will go higher. this maintains a constant load. This maintains a constant mechanical and thermal load on the tool. So your tool life goes up, and so your process time comes down. Why am I telling you this? It's important that when you're cutting super alloys, your tool load has to be as near constant as possible. Because if you vary your tool load, if there's a variation, which means that your mechanical and thermal stresses are increasing, or they are changing very rapidly, and this can be really bad for the tool. Your tool can start chipping, and once it starts chipping, it doesn't take much time to disintegrate on such materials. Right. So let's look at the other peripherals that influence the superalloy machining. The first one that influences is cooling. What kind of cooling should we use for superalloys? And how should our cooling design be? So the first influencers in terms of priority is cooling. Whether you should use fluid, whether you should use air, what should be your cooling design. The second most important thing is the cutting tool itself. So what kind of a cutting tool should it be? Should it be a sharp corner end mill? Should it be a chamfered end mill? Because today there's a fad amongst cutting tool vendors to provide chamfered end mills that they say reduces forces while cutting and improves the life. Or should it be a corner radius tool? All these put together, we need to make an informed decision. The other important thing in tool holding, in cutting tool, is tool holding itself. Should we use collet? Should we use hydro grip? Should we use power chuck? Or should we use shrink fit tools? So we also need to make a very informed decision, and we are going to come to this in our next slides on what and how each one of them would make a difference. The most important, after all, is the work holding. How do you hold your work? Mechanical-wise, hydraulic-wise, holding fixture. So again, this depends on the part, this depends on the design. Because in some cases, you cannot hold a part in vise. You need to have holding fixtures for it. So the design of the fixture becomes very crucial. Let's start with the first one, the cooling. Cooling plays a pivotal role in machining superalloys. Okay? The pressure of cooling is very important. If you have the regular coolant, or what we call as in India we call it as tap cooling. Like if you keep a pipe of water horizontal, the water will fall like a waterfall effect. If that is the kind of cooling that you're going to use, so if I make a drawing of that, this is my tool, and the coolant from this pipe up here falls like this. Okay? If this is how you're going to provide the cooling, I will recommend you not to attempt to cut superalloys, because this tool will not even last the very first contact with the material. The cooling has to be with a very high force, because these materials have very poor thermal conductivity. That means they pass on all the heat to the tool and the chip. So they don't absorb heat by themselves, and most of the times the heat is sent back to the tool. So first of all, you need to have high pressure. We are talking of anything above 40 bar pressure. And the other thing is that if you have this kind of cooling, and let's say you still give 40 bar pressure, so the coolant is hitting the tool at 40 bar. This is still not enough, because the other side of the tool is still open. It doesn't still get the coolant because it is still in contact with the material. You have got this portion of the tool still in contact with the material. So the best way to have the cooling is to engulf it from almost every possible direction. And that's what is shown on the right-hand side. This is one of the most effective cooling designs. You have the tool in the center, okay, and you get 40 bar coolant from every possible side. So you're not leaving any blind spots on the tool. You're covering the entire tool from every possible side to effectively cool the tool and to effectively wash away the chips that are being formed while it's cutting. So the cooling design is very important. Fluid cooling must be used for all superalloys. If you're cutting stainless steel, if you're cutting titanium, if you're cutting Inconel, it must be fluid cooling above 40 bar. For steels, it's different. Steel is not a hard steel is not a poor thermal conductor. It actually is a pretty good conductor. So the heat that is generated is always in the chip. So here, we are not supposed to cool the tool, but we are supposed to evacuate the chip. So in such cases, using fluid coolant can actually become catastrophic for the tool because the tool is slightly hot. So if you try to cool it up immediately, it could have cracks, micro cracks developed. So the goal in steel is to evacuate only the chips. In such cases, we use high pressure air. Air is used to just evacuate. And when you're using air for steel, you obviously do not actually need this kind of a design. This is more suitable for fluid coolant. For air, 4 sides is good enough because it needs to just evacuate the chips. So air coming from 4 directions is good enough for steel. The next one here is about the cutting tool. And this I have actually understood more from Sandvik. What Sandvik suggests is they ask you to use a cutting tool with a maximum core diameter. So if a particular part is being cut, let's say with 12 diameter, they say if the part allows you, go up to 16 diameter because that reduces deflection, especially for titanium, because titanium it has got a lot of spring back inside itself. So it can deflect easily, especially when you're cutting walls, thin walls. So they ask you to use tools with maximum core diameter. The other very important thing, as you can see on your right-hand side, is the fact that the tool must have a corner radius. A tool with a corner radius is much more effective than a tool with chamfer or sharp corner, because chamfer and sharp corner both increase the chance of tool chipping. And you can see on the graph out there, which I got from Sandvik, is that when you're machining a material like Inconel, corner radius R3 tool can give you a tool life of 52 minutes against a 20-minute tool life by a tool which has got a chamfer at the bottom. So you have more than double the tool life and more than 3 times amount of material being removed in the same time with a corner radius tool. So it's important not to use sharp corner tools for roughing. We are very particular for roughing, and not to use chamfer tools. Try and use radius tools as much as possible when you're cutting the superalloys. The other very important aspect here is to make sure that the tools that you're using have got a honed edge. Now, what is honing? Honing is actually making a very fine radius on the cutting edge. If you look at this cutting edge, instead of making it sharp, we actually provide a very fine radius. Once the tool is ground on a CNC machine, it's then sent to another machine which does this very fine honing of the edges. What honing does is it makes the edge extremely strong, okay, so that the chipping doesn't happen. The forces are nicely distributed on that honed edge, so even the force acting is lower. And most important thing is that your cutting life or the tool life extends extremely high. It goes up very quickly. The life goes up. The life comparison between a honed tool and a non-honed tool can be almost as twice. Okay, so as far as possible, use honed tools. I know that not many companies in the world make tools that have honing because that's an additional process. But if your customer is insisting on higher tool life and better cutting, then you must insist him to have tools which have honed edges. Right. After the cutting tool, we come to the we come to the tool holding. You must use either hydro grip or shrink fit or power chuck, because all of these three mechanisms minimize the runout. And if you have minimum runout, it means that you have got a higher tool life. And hydro grip, shrink fit, and power chuck also allows or give you great stability in cutting. And when you have great stability, you can actually have longer tools, and you can actually take much bigger depth of cut than you would take with probably putting the tool on hold the tool using a collet. Also, the fact that when you're using high helix tools on super alloys, the super alloys have this tendency to pull the tool out when you're using high helix tools. So you need to have extremely high clamping forces, and the high clamping forces of the tool can only be achieved by clamping the tool either in hydro grip or in shrink fit or in a power chuck, because the holding area is also sometimes more than 2D or even 3D. So the more area of the tool with a much higher clamping force. The other very important thing I noticed from Sandvik is that they mention very explicitly in their manuals which are for cutting super alloys, is that for every 10 microns added runout, the tool life goes down by 50%. So the holding is extremely crucial here. Hydro grip, shrink fit, and power chuck give you the minimal tool runout. So it's important that even after holding the tool into these things, you need to check if the tool has got a runout. Because if it does, then there's something wrong with the holding, and a runout can actually decrease your tool life considerably. The last one comes from the fact that it's a feature inside iMachining. And this is about controlling the feed rates when rolling on a circle or arc. When programming, the feed rates applied to the tool center, because this is how the feed rates are applied. When you program, whatever feed rate is applied, it's always applied to the center of the tool. If you use the same feed to travel from G1, from this motion to this motion, so if the same feed rate is applied to the center, it's very simple. How many of you have, I believe everyone has seen a merry-go-round. In merry-go-round, the center one that is rotating is actually rotating at a much lower revolution. But as it goes out, the same transition angle or the same angle of movement has to be achieved at a much higher RPM or a much higher feed rate. The same applies even to this. So if you use the same feed rate at the center, that means my periphery has to travel much faster to maintain that feed rate. And when the periphery travels much faster on this corner out here, I actually increase my chip thickness. And this is what we talked about in the beginning, chip thickness variation. So you actually get a chip thickness variation when you're moving on a straight line onto a corner. Okay. Now, in order not for the chip thickness not to vary, iMachining has this unique slider. I don't know how many of us actually use it, but they have this unique slider called the constant chip thickness control for arcs, wherein if the slider is kept at 100%, iMachining will maintain a constant chip thickness at the corner, which means the feed rate at the center of the tool will be much lower in order to maintain a constant chip thickness when moving from G1 to G2. But if I move the slider back to 0%, it means that iMachining will now try and maintain a constant feed rate for the center of the arc. There is an advantage, there is a disadvantage. The advantage here is that The second process, where the slider is at 100%, the cutting time can go up because the feeds drop down a little bit to maintain the chip thickness. Whereas in the case when the slider is at 0%, the feed rates will remain same, so your cutting time will go down. But the flip side is that you will get a chip thickness variation, which means that there is a force change that's happening on the tool. So your tool life could suffer a bit. A word of caution, if you're doing super alloys, don't experiment by putting the slider down to 0 or 20 or 40. Always try and keep this slider at 100% for super alloys. Right. We then come across to a very important concept called machinability of a material. Now, even before we talk about machinability of a material, I would like to bring your attention to another very important thing, and that is the effect of mote width when you're cutting super alloys. Now, let's go into the software. So I'm going to discard the change, and I'm going to open the part. It's already there. So I have this part with a width of 25 millimeter. I have got a slot, and we know that iMachining doesn't slot completely. It does the moting or trochoidal. Now, our general wisdom will say that a 25 millimeter slot, we need to have a bigger cutter, because I just told you that if possible, you go with a higher tool because that avoids deflection. But in super alloys, there's a slight problem when you go with bigger tools, especially in moting. For other areas, it's fine. For moting, if you're using a smaller, bigger tool, you will realize that the amount of time it cuts, comes out, and goes inside, the space for it to do is very less. Now, this space, when it is less for the tool, there is increased amount of stress acting on the tool because it cuts, leaves, it doesn't even must have left, it again re-engages into the material. There must be a nice cutting, it should leave nicely, and it should come back and re-engage itself nicely into the material. Now, the same area, when machined with a 12 diameter tool, I get much more width for cutting. So it has got much more area to cut, leave that cut, go nicely and re-enter it. And the width increases with a 10 diameter tool. So you have to make a decision. If the particular slot allows you to go with a slightly smaller diameter, it would be always advisable to use a smaller diameter than to use a big diameter and try to just cut very fast into that on a very small area of movement. Because this could have a big effect on your tool life. So very important from iMachining perspective, the tool path with minimal movement while moting would wear the tool much faster. So you have to make a decision whether it is to be done with 12 or 10. But if this is the case, definitely not 16, because the area is very less. Okay, we come to another very important subject, and this subject is very much relevant for many of you today, because I have many of my customers in India using iMachining, and they were always complaining initially about the tool life. They used to complain that you have told 4 times, 5 times, but hey, we are not even getting 1.5 times. Sometimes the tool life is less than even what the cutting tool manufacturer suggested. And that all this complaints made us sit back and look at what was really happening. And then we realized that probably we are not paying much attention to the machinability of a material. Okay? Now, what is a machinability? It is basically a term which indicates how good or how bad the work material responds to the cutting process. Okay? In general terms, basically a good machinability would mean that the material is cut with good surface finish, long tool life, low force power requirements, and low power requirements. Cost of cutting is low. But again, this is in the ideal conditions. So there is something that people have come up with called as the machinability index. What is a machinability index? It's basically a formula. The machinability index, Km, equals the cutting speed of the target material, or the material that we are trying to cut, that would ensure a tool life of 60 minutes. Okay? What cutting speed should be used so that the tool life is 60 minutes? That is V60 divided by V60R, which is the cutting speed of a reference material that ensures a tool life of 60 minutes. Now I will explain you this formula because it's very interesting, this formula, because it helps you determine which material is more machinable and which has less machinability. If the machinability factor Km is 1 or more than 1, it means the target material has a better machinability than the reference material, or equal machinability of the reference material, and vice versa. So if you have the machining index less than 1, it means the target material is much more difficult to machine. So how do we use this formula? We use this formula by having a reference material. A reference material in case steels, any kind of steel, is AISI 1112, which has got an index of 1. Okay? Machining of this steel at a cutting speed of 0.5 meters per second gives us a tool life of 60 minutes. So our V60R is 0.5. So this is our reference. 0.5 V60R is our reference. So if we take stainless steel 302, the tool life of 60 minutes for 302 stainless steel is achieved by having a cutting speed of 0.23 meters per second. So our formula is Km, that is the machinability index, equals 0.23 divided by 0.5, which is 0.46. 0.46 is obviously less than 1, so SS302 has got much lower machinability than AISI 1112, that's the reference steel. If we take the same example for AISI 1045 steel, the tool life of 60 minutes is achieved by cutting the steel at 0.36 meters per second. So the formula again is 0.36 divided by 0.5, which is 0.72, which means AISI 1045 has got a lower machinability than AISI 1112. So if you arrange them in logical order, AISI 1112 is the best machinability, followed by 1045, and amongst these three materials, SS302 has got the extremely lower machinability. Now, we know that theories really don't work in practice, because this is mathematics. It does work, but it's not a simple formula. It's not Km is equal to V60 by V60R, because there could be 10 other variables which we have not considered. We just have considered the steel, the cutting speed, and that's it. But why is it necessary to determine the machinability of a material? Why can't we simply just take the UTS of the material as a Bible and just follow it blindly? Machinability determination is important. This is true for cutting aluminum. This is true for cutting steel. This is true for cutting superalloys. This is true for cutting titanium. You must determine machinability before you start cutting parts. Of course, there's a disclaimer here. The process of determining machinability doesn't really suit extremely soft materials like copper and materials like that. And we are not really bothered about those materials at the moment. We are more bothered on harder stuff. So why machinability is important? Machinability is important because it improves tool life dramatically. If you get the machinability right, iMachining can calculate near exact cutting conditions. Trust me, calculates extremely deadly accurate cutting conditions if you can get the machinability right. You have got a much better surface quality because you have calculated the cutting conditions right. For materials which are prone to warpages, if you can get the machinability right, that means you can get the cutting conditions right. This reduces the chance of warpage of the material, and it improves the overall process. So if I go back, is it enough just to have a formula and just use this formula and say, okay, now we are ready, let's do it? It's not, because as I said, in real world, there are several influences that determine the machinability. For example, within the material, today in iMachining, we just consider UTS, but what should we actually really consider? We should consider the basic nature of the material, the brittleness, ductility, etc. We need to consider the microstructure. We need to consider the mechanical strength, which we are doing at the moment. We need to consider the hardness. We need to consider the strength of this material and the amount of hardness that it can reach at higher temperatures. We need to consider if this material is work hardenable. We need to consider if its thermal conductivity is good or bad. We need to consider if this material reacts or has a chemical reactivity or not, whether this material is sticky, whether it can give self-lubrication, for example, cast iron. The level of process parameters greatly influence the machining machinability. Excuse me. Okay, so a lot of these influences the machinability of the material in real world conditions. Cutting tool influences. You change the cutting tool, you get a different machinability. You move, let's say, from Hoffman, you move to Tecutec cutter, you'll have a different machinability. You can't probably use the same parameters. Machining environments, cutting fluids, work holding, they change the machinability dramatically. So there are a lot of factors that are affecting machinability of a material. So how do we determine the real machinability of a material? Because today we have a solution inside iMachining that you can actually change the machinability of a material even after putting the UTS, keeping the UTS constant, because you can have this weird situation. You could have a steel which has got a UTS of 900 megapascals, and you could have a stainless steel which is also 900 megapascals. Does it mean that the parameters are going to be the same or cutting conditions are going to be the same? Theoretically, yes, but practically, no. Why? Because stainless steel, like we saw in our slide before, has got a much poorer machinability than AISI 1112, which is also a steel and probably would have a similar tensile strength. So it's important for us to determine the exact machinability of this material. And to do that, we have got a very simple test that you need to run. And this test has to be repeated for every batch of material, because each batch, let's say 500 pieces, are being cut from one billet. So if the billet changes, the structure could alter slightly. The chemical composition could alter very minutely, but again, that will make impact on the machinability. So let's say your customer is machining 500 parts from one batch of material. So this test must be run once. If the batch changes, let's rerun the test to check if the machinability is same or it has changed, just to ensure that we don't have any issues with our tool life. To measure the machinability of a material, we simply take a block of that particular material. Let's say we want to measure the machinability of AISI 1045 steel. And for that, we take a material, a sample one. You can take 175/50. Simply create the step that's shown here. This step could be about 7 to 8 millimeters or 10 millimeters, because we want the tool to keep cutting for at least 3 to 4 minutes to measure some values. We use a cutting tool. You could use practically any tool. You could use 10, 12, 16, anything. we are using a 12 diameter with 4 flute and 45-degree helix, and the depth of cut is about 24 millimeters, the actual depth of cut. So what we do is we go to the material manufacturer or MatWeb and find out what is the UTS of this material. It could come from the test chart or it could come from MatWeb. In this case, it's about 515 megapascals. So we put 515, and we believe that this is the UTS of the material, and the machinability is same as what the UTS suggests. We then generate a 2D iMachining toolpath for that step. Now, note that our depth here is 24 millimeters, but we need not go 24 millimeter. We go to only a point where we get a whole value as ACP, because we do not want vibrations or chatter to come in between, because that would alter the machinability test that we're doing. It would alter some things and we would get wrong values. So we would like to keep the ACP as close to the whole number as possible. So in this case, a depth of 19 millimeters is giving me an ACP of 2. That's good enough. We don't need to go to 24. The other important thing here is to put it at level 8, because we would like to measure the power on the spindle, because that's a great indicator of the machinability of a material. Once that is done, we go into our modify cutting conditions and we note down what is the power that's going to be required. Our machine has 10 kilowatt continuous, and iMachining is telling me that level 8, it's going to take 5.2. So when it starts cutting, I should see 52% load on the spindle if we are right on our UTS or on the machinability. We could be right on our UTS, but not on the machinability. It's also important to note down the other parameters. So the best way is to take a screenshot of this particular screen and keep it aside, because we are going to use some of these. So the marked value, note down, and we also note down the power. We generate the toolpath, and we take the toolpath to the machine, and we start cutting. Now the cutting has to be in real world conditions. So if you're going to use cooling, you have to use cooling. If you're going to use fluid, you have to use fluid. Everything has to be as though you're machining the exact part, exact production. Once it starts cutting, leave the first 2 passes. Don't do any measurement for the first 2 passes, because you could have some variations in the material size. So the first 2 passes are left. After that, once the third pass it enters, start looking at the load on the spindle meter, okay, till it finishes. Let's assume the load on the spindle meter was being shown as 60% and not 52%, okay, which translates to 6 kilowatt. So 6 kilowatt is being used for cut and not 5.2. What does this mean? It means that as per the UTS and the machinability of the material, we should have had a result of 5.2 kilowatt being consumed on the spindle, but we are getting 6 kilowatt, which means the material is slightly tougher than what the UTS is suggesting. So now we need to figure out what is the machinability of this material, whether it is the same as what the UTS suggests or it is lower. In our case, we know that the material is tough, so the machinability is slightly poor than the target materials whose UTS we just entered. So we go back again to our toolpath, and we then start pushing the machinability factor down. When you go down, you're telling iMachining that this material has got a slightly poor machinability, or the machinability is lower than what the UTS is indicating. So I come to a point where I stop the slider at 16%, minus 16%, save and exit. I go back again and edit the toolpath. And I go back into the cutting conditions. Remember, when you move the slider down to minus 16%, iMachining automatically recalculated everything back to the new minus 16% parameters. So it will always show you a much lower spindle load, but that's not what we want. We want to know if that machinability factor of minus 16% is right or not. To know that, we again bring up that screen which we saved. So we enter in the new toolpath which we edited, we enter the maximum chip thickness of the old toolpath, we enter the maximum VC, and we enter the maximum cutting angle. When this is entered, it goes back again to its old state, and here it comes up again now with the power requirement. It shows that now it is 6 kilowatt, which means the machinability of this material was not 0, but it was 16% more tougher than what the UTS was suggesting. So we will now save that material with the minus 16% value, and then define all our processes with that particular material. By doing that, we exactly get the machinability of the material, and we also exactly get how much, or we also make iMachining's technology wizard determine the exact conditions needed to cut that material in the real world situation. By doing this, you can be assured, 1, your cutting will be much better. Number 2, your tool life will be what we always say, 3 times, 4 times, okay? And the surface quality is going to be much better than what you would have done with that value being kept at 0% and not minus 16%. So if it was the other way around, if 5.2 was what iMachining was saying, and if on the control we were noting that it was 4.8, then instead of putting it on the minus side, you need to push it on the plus side. So it is important that the machinability of the material is determined even before you begin the trials or the machining of any part in iMachining. And this is very true for super alloys, because here a small change in machinability can alter your tool life dramatically. Okay, so this particular test, if anybody has any questions or anything, they could ask me at the end of the session. I can send you the part that I have done, and you could use the same thing for testing machinability of other parts that you have. The other very important thing is that you'll always hear from your customers, prospects, or even from your machine tool vendors who are not well versed with iMachining, is that you exert a lot of force on our spindle because you're going at such a high RPM, such a high cutting feed, such a high feed rate, so much depth of cut. Naturally, the spindle, the axis would be loaded tremendously. Now, you could always give them sales stories. You can say that, no, look, iMachining toolpath combined with optimum cutting conditions ensures constant load, so we don't load your machine. We also ensure that your spindle load is not much, which is a fact. But these are sales stories to the customers and prospects. We also can come up with this story of Hermle, which conducted experiments with different CAD systems to check how well they load the spindle, and they concluded that with iMachining, the forces acting on the spindle are the smallest on all the CAM systems. Makino also reached similar conclusions. Now, this could be sales stories to them. If the customer or the prospect is not a management kind of a thing, and he's very technical, he perhaps will not buy this story from you. But what he's going to definitely sit back and look at is a force measurement experiment that was done with a university in Czech Republic. This university has got dynamometers, a very expensive piece of equipment that measures the forces on spindle, that measures the forces on axis, that measures the forces on workpiece. So it can do all these measurements when the cutting is happening. So for that, they have got a rotating dynamometer which measures the forces on spindle. It can measure an X, Y, Z, and also the torque acting. Then they have an axial dynamometer for measuring load when you're doing simultaneous machining or turning. And then you've got a workpiece dynamometer that can measure the force acting on the material in all sides, X, Y, and Z. And this is placed on the machine table on which the part is mounted. The data measurement is done by some shielded wires, and they use LabVIEW from National Instruments. That's the software that they use to measure this forces. So, what was done in this experiment? A closed pocket with an island so that it could generate that moting motions, or the trochoidal motions. Aluminium, 100 BHN was used. That was the material. An 8mm tool from a solid carbide tool with 3 flutes and a depth of cut of 30mm. That was the AP that we used. Helix angle was 38, and iMachining level was 5. That was a moderate level. We first started with the conventional pocket strategy. The same part was cut using pocketing, our regular pocketing strategy, where we have got a depth of cut of 4mm, a side step of 7.2, and a feed per tooth of 0.09, and every other parameter was taken from the cutting tool manufacturer's catalog. What did we notice on the force? On the force, we noticed that at 4mm depth of cut, the forces that were acting on the tool were about 450 newtons. Okay, and when the tool was ramping inside using helix, it was close to 100 newtons, right? So very important, 450 newtons of force acting on the tool at 4mm depth of cut. Classical pocketing strategy. The same thing was done in iMachining level 5, and they noticed a force of close to 250 newtons at 30mm depth of cut, which is clear that the force generated by iMachining is almost half than the conventional pocketing strategy, and at 8 times the depth of cut. 8 times the depth of cut, we are generating just half of the forces on the tool. So this should give your prospects who are worrying about the kind of load that's acting on the spindle, my spindle will be destroyed. So this could give a calming effect to your customers, to your prospects, saying that, look, we actually generate, this has been measured. We are not talking something out from air. This has been measured, that we generate much lower forces when compared to conventional cutting strategy. You can share this with your prospects. Let me also share you with what we did with Kennametal, with stainless steel and TIL V6, the titanium alloy trials. They wanted to measure basically the tool wear. That was the goal. They wanted to check how the tool wear happens. And the machining was a periphery and pocket, and they used 2 materials, stainless steel and titanium. This was the stainless steel part, a pocket and a periphery that was machined. The first one was done with a 16R3 cutter of Kennametal, and the periphery was completely roughed out and finished in under 3 minutes. Of course, for stainless steel, they were more bothered at the time. They knew that the tool wouldn't wear much, but they were more bothered in the time, and they expected a time of about 20 minutes for this, which we finished in about 3 minutes. The pocket was even more interesting because we completed the entire pocket in about 4.5 minutes. Again, the expected time was half an hour on this pocket for this stainless steel material. For titanium, however, the goal of the trial was not to find what was the time, but to find out how would be the tool wear. So we did the outer periphery machining with a 16R3, but they were more inclined to test another tool, and that was a 12mm tool. After cutting several pockets, what would be the wear structure on the tool? So they cut several parts, and after that, they took the tool out and they put it under magnification, 20 times magnification, and this is what they noticed. There was a wear of about 0.1mm on all the cutting edges, uniform wear of 0.1mm. This was not something that was expected. They expected the tool to have got chipped off on the cutting edge. They expected one of the edges to be broken off, and they expected a much much more damaged tool than what they were seeing in front of them. And they were very surprised to find, first of all, a uniform wear and a very minute wear on the tool in spite of cutting titanium with this particular tool. So this is one experiment. We have another customer whose story you can always also see on your on the website, where 17-minute cycle time was brought down to 3.5 minutes, and overall 16 hours was saved for 75 parts. So that's like saving two shifts of machining, which is big money for the customer. Not to mention the tool life. Also, another trials that we did with this car on Inconel 718 in India on a Herco VMX50. The time ISCAR estimated the tool life was 26 minutes for this tool. We generated a tool life of about almost 86 minutes, 3 times of what they expected to cut, I think, 4 or 5 parts. So our tool life principle or tool life philosophy is being seen here. Another very nice success story that you can see on our website is from Burns Machinery in the US, where we cut Inconel 2625, time savings of 75%, and important, the tool life up by 300%. Klein Oilfield, Inconel 625, time savings of more than 86%, and tool life up by 500%. What is all important here is the fact that your tool life is going up, apart from reducing your time. But what is the cherry on the entire customer success or success in cutting hard materials? The last one, which was done by Mickey and our Japanese team in Japan, was managed to cut tungsten carbide material with a diamond coated tool and brought down the time from 42 hours to 54 minutes. Most important, from 9 tools to 1 tool, because these tools are very expensive. They are diamond coated cutting tools for cutting tungsten carbide. So the entire session that I had today tells us quite a lot. First of all, our solution is meant to cut hard materials. There is no two ways about it. iMachining is meant to cut hard materials. It gets better and better as the material becomes harder and harder and the tool becomes smaller and smaller. You have got to be extremely right about selecting the right cutting tools. Your cooling design has to be near perfect. I've shown you one of the designs. You could have several designs, but the goal is to hit every point of the tool with extremely high force of coolant. The last one was very important, and that is to determine the machinability of the material. If you can get the machinability of the material right, you can actually surpass the tool life suggested by even us. You can get extremely accurate cutting conditions, and overall your process will be much faster and smoother than what would have happened if you had just believed only the UTS and gone ahead and machined it. All right, I come to the end of this webinar, and if anybody has any questions, I would be more than glad to answer your questions. So just feel free to ask me the questions.
Hi, Amod. Thank you very much for this interesting and long webinar. And we don't have so much time now to ask all the questions, but we have many requests to receive this presentation. And I can tell you to our resellers here that such abilities allow us to create a very good relations with machine tool makers, with tool makers. For example, one of the latest examples was from Roku, Japan, machine tool maker from Japan. We have very good relations with them now. They sell their machines with SolidCAM and iMachining. So, guys, this is the unique functionality only we have. Go ahead, and if you have any kind of questions, contact us. Amod, I'll deliver the questions to you. Thank you very much for the time today. It was a great webinar, and we will see you next week, guys. Thank you.
Thank you.